Welcome to The Explainer. Today we're diving into a really fascinating question. What does it take for a robot to not just see our world, but to actually truly understand it?
So how does a robot get to that point of true autonomy? Well, it turns out it's a two-part puzzle that has to be solved at the exact same time. First, it has to build a geometric map of its world. We call that spatial reconstruction. And second, it has to understand what's in that map, and that's vision-language reasoning. And yeah, that's the core challenge right there. The massive difference between just seeing and actually understanding. That's exactly what we're going to break down today. Okay, let's tackle that first piece of the puzzle, the geometry. How on earth does a robot take a bunch of flat, 2D pictures from its camera and somehow turn them into a rich, three-dimensional world it can actually move through? It's a pretty clever process, actually. First, the robot's got to find unique landmarks in a photo, like the sharp corner of a desk. Then, it looks for those same landmarks in all the other photos to figure out how it's moved around. From there, it does a bit of math to pinpoint those landmarks in 3D space, and finally, and this is the big one, it fuses all those points together into one big, cohesive 3D map. But you knew there was a but, right? That last step, the fusion, where everything has to come together, well, it's a massive computational bottleneck. It's pretty much the single biggest thing that slows the whole process down. And this diagram just drives that point home perfectly. I mean, look at it. That final fusion stage is a beast. Just imagine trying to perfectly stitch together thousands of little data points from hundreds of different pictures, all while correcting for tiny errors. It's this huge computational juggling act, and it grinds the whole system to a crawl.
And get this, we're not talking about a small slowdown. This one step can eat up to half, that's right, 40 to 50% of the total processing time. So trying to get this to happen in real time, that's a huge, huge challenge.
So that's the geometry problem. But here's the kicker. Even if you have a perfect, beautiful 3D map, it's basically useless if the robot has no idea what it's looking at. It's just a bunch of dots in space. This is what we call the semantic gap. A traditional system, it just sees the raw geometry, an unclassified blob on the floor. It maps the shape, sure, but it takes a totally new kind of AI to provide what we call semantic insight, to understand that this blob is actually a puddle of water, and more importantly, that it's a slipping hazard. That's the difference. So how do we bridge that gap? The answer is this game-changing technology called a vision language model, or VLM for short. This is the magic key that connects the pixels to their meaning. It's the AI that links what a robot sees with the richness of human language, and that unlocks real, genuine understanding. You can almost think of it like a search engine for the real world. The VLM gets a text query, something like "find a water leak," and it uses this amazing process called attention to focus only on the most relevant bits of the image, kind of like how your own brain would instantly zero in on the problem. And what's really wild is just how much better these things are. I mean, look at this. For a traditional system to recognize something it wasn't specifically trained on, impossible. Zero chance. A VLM, it can hit 70 to 85% accuracy on stuff it's never seen before. And when things are partially hidden, older systems just fall apart, while VLMs are still successful over 75% of the time. It's a whole different league. So, here's the crucial takeaway. Real-time autonomy isn't about solving one of these problems. It's not a step-by-step thing. It's only truly unlocked when you can solve both, that geometry bottleneck and the understanding gap, at the exact same time. And here it is, the elegant solution that ties it all together. To crush that geometry bottleneck, engineers use a technique called spatial hashing, which is basically a super fast filing system for 3D points. And to make the AI brain run light and fast, they use something called quantized attention, which simplifies the VLM's complex math. You put that fast mapping together with that efficient brain, and what do you get? The holy grail, real-time semantic SLAM. And this really is the holy grail of robotics. SLAM stands for simultaneous localization and mapping, but this is SLAM with a superpower. It's the ability for a robot to go into a totally new place and, in an instant, not just build a map and know where it is, but also understand what every single thing in that map actually is. This is what lets it make smart decisions on the fly. Okay, so that's all the theory. Now let's see how all these incredible ideas actually come together to build a real-world robot that can handle complex jobs. So here we go, an autonomous inspection robot. And the easiest way to think about it is that it has a body, that's the hardware, the wheels, cameras, all that stuff, and it has a brain, the AI model payload, where all the real thinking happens. And the body is seriously kitted out.
It's running on a super powerful NVIDIA AI computer. It has multiple high-res cameras acting as its eyes, and it's got a 360-degree LiDAR sensor that gives it this constant, perfect sense of the space all around it.
The brain, though, isn't just one AI. It's actually a whole team of AI models working in harmony. You have the vision language model providing that big picture general understanding. But then it's backed up by other specialists, like a model that's an expert at spotting hazards, like a water leak, even if it's never seen that specific leak before.
But of course, there's a trade-off. All that intelligence costs a lot of power. More powerful AI models need way more processing power, which we measure in TOPS, or trillions of operations per second. A small model might need 6 or 7 TOPS, but a cutting-edge one? It demands a staggering 420. That's way more than a single chip on a robot can handle, and that creates a massive engineering headache.
So while this tech is absolutely incredible, the challenges are still very real. The computational cost is a big one. But solutions are popping up just as fast. Engineers are figuring out how to make these huge models smaller and more efficient, and they're building specialized hardware just to run them faster.
And that leaves us with one last big thought. We are standing right on the edge of a new era, one where robots can perceive and navigate our world with a level of understanding that's almost human. So the question really isn't if this is going to happen, but when and how it's going to change absolutely everything.